Hey Royals, in this video we're going to look at some relative motion in 2 dimensions. Now, relative motion typically in high school deals with one of 2 situations. It's either a boat traveling in a river or an airplane flying through the air. And the problem that we have on our screen right now is simply a boat or a kayaker in a river. And so what I would advise when we look at these types of problems to do first would be simply to draw a picture of the information that's given to us in the problem. So this problem has a kayaker and their paddling speed is 4.5 meters a second. And we're told that is in still water. So this information right here tells us a lot about the kayaker and what we're talking about them. So that would tell me that the kayaker's speed relative to the water, so I would put W here for the water, and we're talking about the kayaker, so I'll say K is equal to 4.5 meters a second. Now, when we're looking at these types of problems, it's important that the variable that is on the left side here, so this K is the object that we're talking about. So in this case here, it's the kayaker. And then on the right-hand side, this W, the variable that we put on that right side is the reference. So this would tell us that the object, the kayaker's speed, so if we look at that V there, so the kayaker speed relative to the water is 4.5 meters a second. Okay, so let's continue reading the question. And we see that we end up getting that the river is flowing at 3.2 meters a second west. Now, the fact that we have west tells us that it becomes a vector. So we have now I've forgotten the number already, 3.2 meters a second, and it was west. And that is a velocity, but it's relative to things. So we know it's the water, because that's the river and it's moving. So the water is moving relative to the shoreline or the ground underneath it. So we can say here of the ground. Okay, so again, just remember that the variable on the left here is the object. So that's the water, and it's moving relative to what? In this case here, it's moving relative to the ground. All right. So this one becomes a vector because we know what direction the water is moving. Now, I told you the best thing to do is always draw a picture of what are we looking at. So I'm going to go ahead and draw a picture. So I know that this might be the north shore of a river. And this might be the south shore of a river. So I'll call that one south. And in between, the river is flowing to the west. So I'm going to draw a vector, and I'm going to draw it with an arrow, and I'm going to say that it is traveling to the west. Now I'm just going to change the color of that blue, just so it shows up a little bit better. So we'll make it a little bit darker, and how about that? That's a little bit better. So that I'm going to call VWG, and it's a vector, so I'll put it above there. And I do have it labeled above, but good practice says let's go ahead and label it here as well. Meters per second, and that is west. Okay, so all the way along between the north shore and the south shore, I do have water that is flowing to the west. Now, what is my kayaker doing? The kayaker is trying to get across. So in the very first problem here, we're told that the kayaker is paddling north. And if the kayaker were coming along and they're going north, because the river is constantly pushing them towards the west, their path is going to end up going a little bit to the west. So let's draw a vector showing exactly what this kayaker is doing. So they're trying to go north. So that would be the speed. Well, I can say it's a vector now because I know that it is north of the kayaker relative to the water is 4.5 meters a second. And I can put here that it's north. Now, when I take these two vectors, let's think about what we're writing here. So if I take the red vector there, kayaker relative to the water, and I add the red vector with the blue vector, so the water relative to the ground, what do I end up getting? Well, the reference point of the first vector becomes the object of the second vector. So I have essentially these two both on the inside. And so when we set up our problems, we want to have the reference of the first vector become the object of that second vector. Because when we add them together, if we look at the picture, when we add these two vectors together, so if we go from the tail of the very first vector to the head of the very last vector, we end up getting the resultant. And that resultant will be the result of adding these two vectors together. So it would be how the kayaker is going to move relative to the ground. So if I was watching the kayaker, and this is them right here, this is the kayaker, they're going to end up moving as they're moving across. So if that's them moving here, they feel like they're moving straight across the river, but in fact the river is pushing them downstream. Okay, so these little kind of yellow teardrop shapes show us how the kayaker is going to be viewed if we were in a helicopter looking straight down at that kayaker. Okay, so this equation here is going to help us try to visualize what's going on in the problem. Okay, so I'm going to just get rid of my drawings of my kayaker. And there we go. So I got rid of all those. How do I find this hypotenuse or this purple vector? Well, we see that it is a right angle here. So there's my right angle. And I know from mathematics that this right angle triangle can be solved with primary trigonometric ratios. So sine, cosine, and tangent. I also know that is a right triangle, so I can apply the right angle triangle theorem, also known as a squared plus b squared equals c squared, to try to find this long side, this purple side of my triangle, which we are going to label as VKG. Okay, so when we try to use this a squared plus b squared equals c squared identity, we are actually finding the lengths of these sides of the triangle. So I'm going to say that I'm going to go VKG squared is equal to, that's like saying c squared equals, one of the legs of the triangle, so the red or the blue vector, so let's say KVW squared plus WVG squared. Now I'm not putting vector symbols on them, again, just because they are lengths. So this is like saying a squared plus b squared. We're not going to write this out. This is what I wrote here. I wouldn't write because this line here is actually the physics that we're doing right now. So let's substitute in the numbers that we do know. I don't know what this KVG is, but I can solve for it. I can say KVW, that's right here on my screen. That's 4.5. So we're going to say 4.5 meters a second. And again, I don't care that it is north because we're only looking at the magnitudes or the lengths of the sides. Squared plus 3.2 meters per second. And I'm going to square that as well. Okay, so when I take these two, and I'm going to just pull up my calculator, I'm going to type in 4.5, square it, plus 3.2, square it, I end up getting a number of 30.49. That's going to be meters squared seconds squared, because I've squared my units there. That's KVG, and that's squared. So when we take the square root, what do we end up getting? I find that the magnitude, the length of that purple vector which is the kayaker relative to the ground, the speed that they travel is 5.52 meters a second. Well, that's half the story. That just tells you how fast they're moving. I need to know in what direction. If I was in that helicopter, what direction are they moving? Well, this is the angle I'm always going to look for. The angle relative to where I started. So right at the shoreline. If I'm looking at the shoreline and I point, what direction is the kayaker going to end up? That's right along that purple line. So let's find that angle. So if I'm looking at the triangle that I have information about the opposite side. I have what we would call the adjacent side, which is the KVW. And I actually, in fact, have the hypotenuse as well. I'm going to use tangent. Tangent theta is equal to the opposite length. In this case, the opposite to that angle is 3.2 meters a second. Adjacent to it is 4.5 meters a second. And if we use the opposite angle the inverse angle of tangent of 3.2 divided by 4.5, they're both meters per second. I end up getting a number. Let's find out what that number is. So I'm going to type 3.2 divided by 4.5. Inverse tangent of that answer, I end up getting about 35 degrees. So my angle is 35 degrees. So we have the two pieces of information. Let's put them together. So I have an angle, 35 degrees. I have a magnitude of 5.52. Let's put those together. All right. So how do I report that speed, that velocity that kayaker is moving? Well, I'm going to zoom out slightly so I can see my picture, and I'm going to say, therefore, VKG, so the velocity of the kayaker relative to the ground, is equal to 5.52 meters a second. There's the magnitude. Now let's give that direction. So the direction we know is 35 degrees. But relative to what? Well, in the picture, I start north. And then from the north direction, I'm rotating towards the west. So I start north and I rotate to west. So that means my direction inside my square bracket, I'm going to write north 35, because that's how much I rotate, towards the west. And there we go. There's my answer for the first part of this problem. That we know that the kayaker relative to the ground is moving at 5.52 meters a second, north 35 degrees west. Now let's look at what the B part question is saying. It says, how long does this take? How long does it take the kayaker to get across the river? Now I want you to think about this picture that we have. And that's this picture right there on our screen. That picture, I know how fast they're moving along that diagonal. I don't know how long that diagonal is. I know how fast they can move in still water across the river. And I also know how wide the river is. I didn't draw it on my picture, but I'm going to add it there. In the question, they told us the river is 220 meters wide. Okay, so 220 meters wide. And that's going to be north. Like if I'm thinking about how far I have to travel, that's 220 meters north. So why don't I pick the dimension or the value of speed that is also in that direction? Okay, if I knew the length of the hypotenuse, I could possibly use that to find how long it gets across. So I'm going to use the two directions that are the two values that have the same direction. Okay, so for B part here, let's do that. B part, I'm going to remember that speed is equal to distance or displacement divided by the change in time. I remember that. So let's bring that into relative motion. Well, I said the velocity we're going to use is the one that's in the north direction. So that's the kayaker relative to the water. And the displacement we're going to follow is that one that's also in the north direction. So that's going to be the delta D, and we're going to say in the north direction. And then we're going to say delta t. That's what we're trying to find. We're trying to find this time. So let's substitute the numbers that we do in fact know. Well, the kayaker relative to the water, from right there on my page in the orange box, is 4.5 meters a second, and it's north. So 4.5 meters a second, and it is north. Now the distance, or the displacement that I'm going to end up going, that's 220 meters, and that is also north. And then I'm going to divide it by time. We'll do a little bit of rearranging here. So we'll say delta t is going to be equal to 220 meters, and that's going to be in the north direction, divided by 4.5 meters a second, and that is also in the north direction. Cool. So let's take those two values, let's divide them. So 220 divided by 4.5, and I end up getting about 48.9 seconds. So we can say 48.9 seconds. All right, so we now know how long it took to get across the river. Now, what I want you to realize is this time is going to be the same if you were to go along that hypotenuse. So what I'm saying is this time to get across the river, if this was my river, is going to be the same time it takes to go directly along that diagonal. And that's a problem that most students have difficulty wrapping their head around. And what I want you to realize is that this speed, we'll say the kayaker relative to the ground, is slower than the speed of, oops, this is the kayaker relative to the water, I apologize. This is the kayaker relative to the ground. The kayaker relative to the ground is going to be moving faster because it is the hypotenuse of that triangle. So if they're moving faster and they go a larger distance, the length of my blue line is longer than the length of the black line, they actually will come out to be the same time. Because that makes sense. If this was my kayaker as they moved across, at this point here, they're still going to be side by side. Because the components in that direction have to be the same. Right? So they're moving across the river. They're moving vertically up my page at the same rate. So if I'm here, I'm going to be there. And that means that when I get to the other side right there, it's going to be the same time. So you can see that these two line up, these two line up, these two line up, and that one lines up. Okay, so as we move across the river, those two vertical parts will be the same time. Okay, so it doesn't matter which, if I go along the hypotenuse, if I know that length and I use that speed, or if I use the vertical part here and I know that distance as well, I'm going to get the same time here. Okay, so C, let's take a look at C. Where will the kayaker land relative to the starting position? So I want to know, where is this point right here relative to that point? So that's a fancy way of saying, what is the displacement of our kayaker? Well, what I want you to realize, let's take our picture from above here. Let's take this picture. I'm just going to duplicate it so I can move it down my page. So let's duplicate it here and we'll move it down, because I'm going to use this picture again. Where did it go? There it is. So let's move this down to right there. And I'm going to erase this piece here, and I'll erase the arrows. And I'm going to say that this picture was for speeds or velocities, right? But the funny thing is, this triangle is a similar triangle to the displacement one. So that displacement of 220 and this piece here will have the same angle on the inside. So this theta that's here will be the same. I can take the speed part here. That is also the same relative scaled length to 200 meters, and it will be in the north direction. right? So there's two approaches that we could do here. I know the angle. We found the angle earlier to be 35 degrees. So this was 35 degrees. I can say, hey, I have the adjacent side and I'm looking for the hypotenuse side. That's one approach, by recognizing that the speed triangle, this one here, and the displacement triangle are similar triangles. That's totally valid. And let's go ahead and do it that approach. So I can say, hey, I have adjacent and I'm looking for the hypotenuse. So I can say sine, oh no, that would be cosine. Cosine of 35 degrees is equal to adjacent 220 meters divided by, and let's call this delta D. And I'll say delta D. Okay. Delta D cosine 35 degrees is equal to, actually this shouldn't be a vector because primary trigs only give us lengths. 220 meters. Delta D is going to be 220 meters divided by cosine of 35 degrees. Let's punch that through a calculator and find out what we got. 220 divided by cosine of 35, we end up getting 268.6 meters. So delta D is going to be 268.6 meters, which allows me to say delta D as a vector is 268.6 meters in what direction? Well, north, 35 degrees west. That's one approach. Okay. Another approach could be to find that that velocity of the kayaker relative to the ground. And we already know that. We know from part A that this speed was 5.52. So this was 5.52 meters a second, and it was in that direction of 35. And it took us, the time to get across the river was 48.9 seconds. So if I say delta D, distance or speed, V is equal to delta D divided by delta T, and we can actually call these vectors because we can find the displacement, that velocity, the red velocity there, is 5.52 meters a second north, 35 degrees west. So that's delta D. And we divide that by this time of 48.9 seconds. All right, so let's take our numbers and we'll solve for delta D, which means I'm going to multiply 5.52 times 48.9, and lo and behold, we get 269.9 meters north, 35 degrees west as my delta D. And you're going to say, wait a second, those are slightly off from each other. These two answers are close. One used the speed along that hypotenuse, and I'm highlighting that right now, times the time it took to go along that hypotenuse. That's what I was trying to argue here, that the diagonal length might be longer, but the time you get across is going to be the same. You can see that, in fact, you do get relatively the same answer, and they're off because, of course, I had to round my time a little bit, and I also rounded the speed a little bit as well when we calculated it in part A. So either of those two answers would be acceptable as the approach I would take when solving it using physics. Okay, so let's look at D. D says if the kayaker wanted to land straight across the river from their initial position, what angle would they have to aim at? Okay, so let's think about that part. D. So D, if I have my river here, there's my river, here's my starting position, and here's my ending position. Oops, end. I want to go straight across the river. That is what I would love to do, right across the river. And I'm going to just move my end piece just so that the dot is actually on the arrow. That's what I want to happen. I want the kayaker to move straight across relative to the ground, right from the south shore, south shore to the north shore. Now the problem is the river is flowing. Now if the river is still flowing to the left, west. So this river is still moving to the left or west. So that means if I were to go straight across, if we aim straight across, we're going to end up going west. We miss. We end up going west. So how do I fix this? Well, if I was thinking about this, the water's always going to push me towards the west. It's always going to push me over this way. So if I aim east, if I were to take my kayak and I point it towards the east and allow that water to push me to the west, I end up going straight across the river. So let's think about that. That says that the speed, this one here, that the velocity of the water relative to the ground, and the red one here is the velocity of the kayaker in the water, because that's what I'm going to do. I'm going to kayak along the red line so that when the blue river pushes me back, I end up going straight along that black arrow. Okay, so how do we get the angle here? How do I get this angle? Well, the river's not changing its speed. The river's still going to be moving at 3.2 meters a second west. 3.2 meters a second west. The kayaker is still going to be able to move at 4.5 meters a second. In this case, it's not north. It's still 4.5. Now I'm just making sure. Yes, 4.5 meters a second. In this case here, the angle is not known. And we actually don't know how fast the kayaker will move relative to the ground. That's my black arrow. We don't know that. So how do I get that angle? Well, I have the opposite side of the triangle, because this will form a 90 degree. I have the opposite side, and I have the hypotenuse. So sine of theta is going to give me opposite 3.2 meters a second divided by hypotenuse 4.5 meters a second. Theta is equal to sine inverse of that ratio, 3.2 divided by 4.5. Let's put our meters per second and meters per second and go 3.2 divided by 4.5, and we end up getting sine inverse of that. We get 45 degrees. That means I have to point my boat what way? Well, I started it in the north direction. I started pointing north, and it rotated towards the east. So I'm going to say that the direction is going to be north 45 degrees east. That's what direction I need to point my boat in order for the current to push me back so that I end up going straight across the river. Okay, you'll notice that this angle, 45 degrees, is not the same angle that we got earlier of 35. And this is because part of my speed or velocity is getting put into fighting that current. Okay? All right, so if you have any questions or concerns about this video, please do not hesitate to reach out to us.